Tonight, we are fortunate to have as our speaker, Brian Swingle, professor at the University of Maryland. Brian is one of the young stars in the study of many-body quantum entanglement. Indeed, he played a key role in launching the widespread interest in this topic among physicists today. His ideas are influencing how we understand the flow of electrons in materials, and also remarkably, how quantum mechanics influences the flow of information near black hole horizons. Brian obtained his PhD from MIT in 2011 and held postdoctoral positions at some combination of Brandeis, Harvard, MIT, and Stanford before joining the faculty of the University of Maryland in 2017. Please join me in welcoming Brian.
Thanks. Thank you for that very kind introduction. Thank you all for braving the snow to come out and hear me. Thank you to the Aspen Center for Physics and the Opera House for hosting this great event. And thank you to all of my physics colleagues who have made the conference so far a really great success, in my opinion. I happen to be one of the organizers of the conference, so I invited myself to give this talk. So hopefully that wasn't a mistake. So my task today is to tell you about a little bit about how chaos enters in the description of quantum systems. So I'll actually explain a little bit about what I mean by chaos and also what I mean by quantum. But to start out, you should think of chaos in terms of, you probably heard of the butterfly effect, where you imagine you have a small change somewhere, maybe a butterfly flaps its wings, and then somewhere else, a day later and a mile away, a tornado develops. So small changes can have big effects down the road. That's kind of the idea of chaos. And then the idea of quantum is that you're familiar with the sort of ordinary rules intuitively of our world. You have things bounce around, you can walk, you have a definite position, a definite speed. But we know that when you make things small enough, when you look at electrons or single atoms, that they play by different set of rules, the so-called weird rules of quantum mechanics. And so what I'm going to try to explain a little bit of, give you a flavor of how these two things interplay in this sort of exciting new developments that have been taking place. Okay. So yeah, this is the actual conference that's happening. We're particularly focused on what we call many-body quantum chaos. So that means quantum chaos, so chaos plus quantum mechanics, plus lots of stuff, lots of particles interacting together. And as Subir said, this has been a really great conference because it brings together lots of different communities. It brings together scientists who make experiments of novel and exciting types, and it brings together scientists who just think about those experiments and try to understand the physics of what's happening in those different experiments from all different sets of communities. So people who think about gravity, about Einstein's theory, about space-time and black holes, people who think about material properties, people who think about doing quantum computation or quantum information, and all this is coming together on the subject of many-body chaos. Okay, so the plan for today is to tell you a little bit about quantum and chaos, what those two things are, tell you about then the main idea of the butterfly effect, the quantum butterfly effect, so how quantum mechanics modifies that story. And then I'll tell you some connections and directions that we're thinking about right now, things that we were talking about at the conference, about how you can measure this quantum butterfly effect, for example, by effectively rewinding time. I'll tell you about how the quantum butterfly effect is manifested in new kinds of speed limits that might be of relevance to understanding the way electricity and heat move in materials. And at the very end, I'll tell you a little bit about how quantum butterfly effect and quantum chaos are manifested in the properties of black holes. Okay. So I think this is part of the excitement, is that all of these different things, these novel kinds of experiments, interesting solid state properties, material properties, and even the properties of space and time are kind of all brought together in this subject. Okay, so that's the plan. So let's start out then with the butterfly effect. Okay, so butterfly flaps its wings. Here you have a tornado. But this is an evil butterfly. It is a nefarious intent. It's very happy to use its power, I guess, to destroy its enemy in this house. Okay, so our idea is kind of similar. Of course, we want to understand the butterfly effect, how it can happen, how these small changes can have big effects, but we also want to use the butterfly effect to understand the physics of other things, understand how it feeds into other physical properties that we care about. So we are interested in using the butterfly effect, but hopefully to more noble purpose. All right. So this is all classical so far. This is a classical butterfly. Here's a picture of what's called a classical billiard. So you can think about this as being a boundary here which is perfectly reflecting. And inside this boundary, I start a bunch of particles. These particles are all nearby initially. So the difference between different particles' initial condition is only a small change, right? But what you see, if I go back to the start here, is that while they start together, so they're sort of bouncing together, as they go, they get further and further apart. They kind of go all over this stadium. And eventually it looks like a complete, for lack of a better word, chaotic mess, okay? So even though everything began very close together, at the end of the day, you got something very, very complicated. And actually, this particular kind of stadium, this so-called billiard stadium, is actually a situation that was studied in detail by one of the participants in our program, Professor Bunamovich from Georgia Tech. And so it's been really exciting to bring that sort of very old study. This happened many years ago, and to try to make new connections. Okay, so that's classical chaos. That's all you're going to get, 2 slides, so hopefully it makes sense. But if we go back to this butterfly, when the butterfly flaps its wings, well, we know that wings are composed of various kinds of organic materials, like carbon, oxygen. And so when these wings move, like there are trillions of atoms that are moving, and moving by amounts that are much bigger than the size of the atom. So this is like a huge change from the point of view of these atoms. So we could ask what happens if we scale this down, if we go down to lower and lower size, so that we're not changing trillions of atoms, or even thousands of atoms, or even tens of atoms, but a single atom. That's sort of the ultimate quantum limit. And once we're talking about single atoms, then we have to use the rules of quantum mechanics instead of classical mechanics. So let's talk about what those rules are. Okay. So maybe at least the physicist Richard Feynman said that the double slit experiment is kind of the keystone of quantum physics. So here's that experiment. You have a source of quantum particles. Electrons are such particles. So this red thing you can think of as shooting particles to this screen down here. And on this screen, we're going to look and see where the electrons land. And we put another screen here so that there's only 2 ways electrons can go. Roughly, they can go through this slot or this slot, right? Think about this as just being 2 holes punched in a 2-dimensional sheet. And the way I like to think about it, the key feature of quantum particles is they like to keep their options open to them. They don't want to choose just one path. They kind of want to try all the possibilities. And so the rule, which can be made mathematically precise, is that the electron that's emitted here tries all possible ways of getting from the start to the end, and that these ways combine in a non-trivial way. It's sort of similar to the way that waves of water on the surface of a pond can interfere. You can have the crests add up, or they can cancel with a trough and give you nothing. And so if you send these electrons through a single slit, you'd see something like this. They just more or less pass through and give you a strong spot, right? Because there's only one way to go, so there's no possibility of anything interesting happening quantumly, because we restricted the system to only have one option. So even though it likes to keep its options open, there's only one option available, and it only does one thing. But once I give it 2 options, then somehow it tries to do both things, or it considers both possibilities, and you get what we call interference pattern, where, for example, there is a big chance the electron can end up here, but if you do this experiment many times, you shoot many electrons, you find that actually there's a chance they can end up over here instead, sort of far away from the central position. And there are also places where the electron is never found, no matter how long you look. And that's sort of the key feature of quantum, is that these electrons take these different paths, and these different paths combine in a non-trivial way to give you some interesting pattern of detection here. Okay. But this is kind of a complicated situation. The electron can move around in space. To make things simpler, what we'd like to do is put these electrons in just one location and study just their internal properties. So what is possible to do is to actually, via some combination of magnetic fields or electric fields or other kinds of confining potentials, you can actually freeze particles like electrons into certain positions. So here's actually a picture, which I'll talk more about later, of beryllium atoms. So beryllium is an element. This is beryllium atoms where you've removed one electron, so they have one positive charge. And by a clever combination of magnetic fields and electric fields, we can arrange for these beryllium ions to be stuck in place in this kind of crystalline arrangement. And so once we do that, we don't give the beryllium ion anywhere else to be. It can only be in one place, so we know where it is. That's set. But rather remarkably, this beryllium ion still has some internal structure. It still has two different possible states it can be in. You could think of them as being up or down in terms of, or 0 or 1 to use a sort of computer-y notation. So think of it as a bit. The beryllium can be in some state which we call 0 or some state which we call 1. Okay, there's only two options. So this is sort of the simplest possible case. Okay. But these are quantum particles, and so, as we said before, the rule is that we have to let them consider all the possibilities. And it turns out that in quantum, the possibilities are not just 0 and 1, but sort of any combination of them. In fact, you can think of that, if you want a picture, as like the surface of a ball, where at the top, the north of the ball, you have 0, at the bottom you have 1, but actually this quantum bit, or qubit, can be anywhere along the surface of this ball. So any point on the surface is a valid configuration of this quantum bit. So you need two numbers, like a latitude and a longitude, to tell you what the state of this quantum bit is. And so we've reduced the system down to this sort of elementary unit. And now we want to think about adding lots of these things together. So if I only have one qubit, I said I need two numbers. If I look at, say, two of these ions at once, then it turns out I need 4 numbers. If I look at 3 of them, I need 8 numbers. If I look at 4, I need 16. The pattern is that the number of numbers I need to tell me the full state is doubling every time. So actually, very quickly, even if you wanted to describe the state of a few hundred of these qubits, that's a very small system. You would need more numbers than there are people on the planet, right? In fact, it's really, really vast. To give you a sense of how vast it is, let me give you a little way to think about it. So here's a picture of the faint residual light that's present everywhere you look in the cosmos. This is called the cosmic microwave background. So every direction you look in, you see faint residual light, which came from a time in which the universe was too hot for light to propagate. And as the universe cooled down, there was a point at which now light could move, and then that light moves towards us, and we observe it. And so this represents sort of the edge of the visible universe. It's how far out we can see out. Now, if you filled that whole visible universe with the best possible hard drive that we can make now, so all of space, 13 billion light years on a side with this hard drive, you would have 10 to the 97 classical bits, roughly speaking. This might be a little bit better now. Now, that will only let you store or know the state of about 300 qubits at a time, right? So there's some kind of incredible vastness or richness about these quantum mini-qubit systems that we'd like to understand, okay? And so this leads to the idea of what I like to call the complexity or entanglement frontier. So the idea here is you've certainly heard about the Large Hadron Collider in Europe, in which we're colliding together particles at very high energies to probe the fundamental constituents of matter at very short distances and very high energies. So we could say that that Large Hadron Collider, or LHC, is probing the energy frontier. It's pushing our knowledge of the universe to higher and higher energy. Similarly, our astronomer colleagues who look at the cosmic microwave background, they're probing our knowledge of the very early universe. So that's like a sort of time frontier. It's how far back in history we understand what's going on. But here, with these complex many-qubit quantum systems, there's a new kind of frontier. There's a kind of frontier of complexity. Whereas we put these things together, we have more and more possibilities, more and more options, and remarkable new phenomena can arise. So superconductivity, Bose-Einstein condensation, even black holes can actually all come out of these complex quantum systems. Okay, and so this is sort of a major effort now that many physicists and other kinds of scientists and engineers are thinking about, is how can we understand the edges of this complexity frontier, how can we push it forward, and how can we use it to do interesting things? So for example, the quest to build a quantum computer. This is a new type of computer that operates according to the rules of quantum mechanics and can do new kinds of calculations that you could never do otherwise. The quest to build this kind of device is firmly at this entanglement frontier. So this is a picture of a chip which is manufactured in the lab of the Martinez group, which is working with Google now to build a quantum computer. I won't tell you what's going on here, but this is sort of one nice picture. And then I really like this kind of art here by Christian Greilingen, sort of people considering this kind of cloud of possibilities, all these different particles put together, there's all these different options that they can be in, this vast space of possibilities, and we have these sort of very complicated material apparatus here. We're trying to probe what's going on here and understand the physics, and it even maybe connects to the cosmos in some way. So that's all very exciting. Okay, so that's kind of the context. We're interested in understanding this complexity frontier, and what this conference that we're organizing this week is particularly about is the way that chaos manifests in this complexity frontier. Okay, so let me tell you now about the quantum butterfly effect. So here's the thought experiment that we want to think about. We have two situations that we want to consider. Imagine you have a movie or something, and you can play the movie forward. That'll represent by a curve which starts here and goes forward and ends there. And I call that time runs forward. But it's a movie, we can also rewind the movie, and in which case we'd start at the place that we reached and go backwards. And if we don't do anything, then we end up exactly where we started from, right? So if you go forward and then backwards, nothing happens. That's like doing nothing. But what about if we let the butterfly flap its wings, right? Then we could imagine going forward like this, making a very small perturbation, a very small poke. Maybe we just touch one of these qubits a little bit. That's the butterfly. But then what we find is that if we let time now run backwards, if we try to rewind the movie, we find that we don't end up where we started from. We actually end up in a totally new place. And the difference between the starting point and the ending point, the fact that it grows, the more I run time forward and then backwards, that is one way of characterizing the butterfly effect. Okay. So our job is to understand how this butterfly effect manifests in these systems of many qubits. Let me give you an analogy. I hope you've all had the pleasure or pain of trying to assemble an IKEA furniture before. Sometimes it can feel like it doesn't quite make sense. And maybe you even had the experience where you get to the 34th and final step of your nice cabinet here, and you're very happy, and then you look down and you realize, oh no, there's a screw. And you say, where did this screw come from? And you think, and you think, and you think, and you look through the instruction manual that has no words in it, and you realize that, oh, you missed a screw in step 2. Well, maybe if you're really good, you can find a better way of doing it. But as far as I'm concerned, the simplest thing to do is you've got to undo all the steps. You've got to go from step 34 back to step 2. You've got to put the screw back in there, and you've got to rebuild it again, right? So that's what's happening here. In order to undo this, I've got to take the whole thing backwards, pat the screw back in, and then go back, and that's the only way I can get back to the whole cabinet. On the other hand, you can reason to yourself, well, this cabinet looks pretty cabinet-like, whether I have the screw there or not. Maybe it doesn't matter if I have that screw. Maybe I can just put the screw in a cabinet of another type and forget about it, and it'll still be a perfectly fine cabinet. And as long as it's not a crucial load-bearing screw, you're probably fine. So this is actually kind of like the billiards we saw. It doesn't actually matter where you started from. Everything ended up looking very kind of regular and uniform and chaotic at the end of the day. This is another property of chaos. It's the property the system kind of forgets where it started from. If I showed you that picture of the billiards, you would have no idea where I started those particles from. It's totally impossible to tell. And in the same way here, maybe you can't really tell whether the screw is there or not. So the state of this whole cabinet is very different because the screw is there and it's very hard to put that screw in. But on the other hand, if you just sort of want it to hold things, if that's what you're caring about, maybe it doesn't matter too much. Okay. So now I want to give you a slightly more precise and pictorial representation of how this spreading happens. So I'll draw what we call a space-time diagram, in which I put space along the horizontal here, and time along the vertical. And each of these lines is like the state of one qubit over all time. So when the line just goes straight up with nothing happening, it's like the qubit's just sitting there, you're not doing anything to it, nothing's changing. And I have a set of them. So I have a bunch of different qubits here because we're interested in some mini qubit system. Right. So now I want to talk about how the interactions work. I want to represent the interactions of these qubits by these rows of boxes. Okay, and I'll call this the forward evolution. So what you should think about is the following. So imagine we take a row of the opera house here, and every other person is special, and you all have some balls, say, or something you can exchange with each other, some information. And so the rule is at the first time step, you look to your neighbor to the right, and you can exchange a ball with them or not, right? So you pair up in this way, you talk to your neighbor, and you can exchange some information or give them a ball or get a ball from them. And then at the next step, you look to your neighbor to the other side, and you do the same thing. And you simply alternate this over and over and over again. Right? This is a way of sort of communicating across the whole system, because if I say start a ball on the right side of the house, then by taking these steps, slowly you can get the ball all the way to the other side. Except, of course, these are going to be quantum balls, so we have to think about all possible ways that they can move across the rows of the opera house. Okay. And you should think of these little orange boxes, just like the qubits themselves sort of want to keep their options open. What these orange boxes describe or encode is all of the set of possible ways these qubits can interact. So the different possible outcomes that you can have. So you sort of think about putting in a set of possibilities down here. You do some operation, some interaction, some exchange in this layer, and you get a new set of possibly modified possibilities out up here. Right? So it's like a computational rule, like a computer program. Okay, and just like I have these forward bits here, I can also have the backward bits, which is just doing the reverse. So just like I can rewind the tape in a classical movie, I can also reverse whatever quantum interaction happens between these particles. Right? And so this is like step 1, step 2, step 3. 1, 2, 3, 4. And then this is step 4 in reverse, step 3 in reverse, step 2 in reverse, and step 1 in reverse. So that's what this picture means. And okay, let me tell you how to manipulate this picture. The key property is that these purple and orange boxes cancel out. Okay? So I can take that, the fourth step and the fourth step reversed, and they cancel. So I'm just rewinding the movie. I'm moving the movie forward and then backwards, and nothing happens. And similarly, I can cancel the third step, forward and backwards. I can cancel the second step, forward and backwards, and the first step, forward and backwards, until I have nothing left. Right? So this is, again, doing nothing. Okay, so that's the first side of the butterfly expect experiment. But now let's put our butterfly into the mix. And as I said, we'll make it a very quantum butterfly. So I'm only going to address a single one of these particles, a single qubit. And I put my butterfly there. And now I want to see what the effect is of this butterfly. After I do this time evolution, I go forward in time, apply the butterfly, and then go back in time. Well, I can try to cancel again. And many of these boxes are going to cancel. But there's a rule which says that if there's something in the way, then the two boxes, they can't exactly cancel. This is the effect of the butterfly. It's made the rewinding not quite possible. But you see, it's still only a very small, local effect. You're only affecting two of these quantum particles now. But I'm going to color that blue because it's like a new sort of bigger butterfly, a bigger blockage. Right? Now, I can keep doing this procedure. I could cancel that second row there. But now, because originally the blockage was just on one qubit, now it's on two, but now the bigger blockage blocks even more of these gates from canceling, these different interactions. So now I should color those blue as well. Right? And I can keep doing this, but the blockage grows again, and I can keep doing this, and the blockage keeps growing. And the longer you go forward in time before you apply the butterfly and then try to go back, the bigger the blockage is going to be at the end of the day. So although you at first tried to just perturb a single quantum particle, already after only 4 time steps, you've sort of infected or perturbed 8 different particles. And the longer you go, the more you'll disrupt the system. Okay. Now, that was the case where you talk to your neighbors. We could consider another possibility where it's like a dating event where you randomly pair up with people and see if you're compatible, or where you call your friends long distance on the phone. Right? So in this rule, in this way of interacting, you don't have to talk just to your neighbor, you can talk to anyone. But the rule still is that I pair up the different quantum particles together and I let them interact. So for example, this is a valid pairing. I take this particle and it interacts with this one interacts with that one with that one, and so on. And you allow any possible combination. And now, because it's hard to draw, I'm only going to show you snapshots at fixed time instead of showing you this whole time history. Okay. That's another possible interaction. You have all these different possibilities. So let's put our butterfly in here and see what happens. Well, suppose that's the first set of interactions you get. This is the first pairing. So now this butterfly, it's going to block this interaction from canceling, just like in the previous picture. And so after that interaction happens, we should color that new particle blue because it's part of the blockage. And similarly, if we have now another random pairing, it's very likely this will be between some new different particles. Well, then the blockage on this side and this particle and this particle, are going to spread to these new particles. So now the blockage grows. And if I have another interaction pattern, which is another random choice, then you see now actually there are 1, 2, 3, 4 new particles that are blocked. And if you play this game enough, what you'll realize is that the size of the blockage, the effective region, again doubles every time. So it's again a kind of growth, but actually it's growing more rapidly. Whereas in the local case, when you only talk to your neighbors, the perturbation, the size of the blockage grew linearly with the number of steps. Here it's growing, it's doubling every time. Right? Now, if you look at the classical butterfly effect, you look at the mathematics of that, there's a quantitative version of the statement that small changes have big effects. And that's the statement that in a certain precise sense, the difference between these different things, these different possibilities, doubles every time unit. Okay. So that doubling that you get in the classical butterfly effect is very similar to the doubling that you get in this growing quantum blockage. And so this is the reason why people propose that this kind of growth of the butterfly in this quantum system is an analog of the classical butterfly effect. Okay. So now let me tell you finally how you can think about probing this, how you can see where the blockage is. And the idea is to try to do some other thing to the system and ask whether it matters in what order you do it. So, for example, suppose you want to apply some kind of transformation to this qubit here. You want to know, does it matter whether I do the transformation first here and then apply all this complicated forward and backward stuff? Or do I do the forward and backward stuff first and then apply the transformation? But you see, because there's nothing on this line, this box can just go down, nothing happens, so it's equivalent. So in other words, by testing whether the order matters, you can tell whether this butterfly has spread to the location of that qubit. By contrast, if you put the probe here, well, now there's a little, at least some chance, some possibility that the blockage is going to affect this. And so you try to compare doing it before and after, and the color changes a little bit, which is my way of indicating that it's different whether you do it before or after this complicated forward, backwards butterfly thing. And in fact, because there's more possibilities for the butterfly to spread to the center region, the effect actually grows the closer you get into the center. Okay. Now, because I'm a theoretical physicist, I have to have an equation in every talk I give. So I've chosen a very daunting-looking one. This is how you represent mathematically the pictures on the previous slides. Okay. So hopefully you appreciate me saving you this. This is just to show you that there is a very precise formula. The different terms here actually account for the different possibilities we talked about, whether the thing spreads or not. And at the end of the day, you can use this mathematics to calculate very precisely what you expect to see. And so if you have, again, space and time this way, then what you expect to see is indeed that you start with a small perturbation. If these blue blobs are the size of the perturbation and its strength at different times, the perturbation starts small. It has a very small extent. Then as your time goes past, it gets bigger and bigger and bigger. But more precisely, it's very small out here, and actually the strength of the perturbation, the strength of the blockage gets bigger the closer you get to the center. And so this is the kind of thing that we could try to do an experiment to verify, to test this butterfly effect, to see if a system is quantum chaotic or not. And in fact, there are two related questions. The first question is, how do you actually measure it in the lab? And the second question is, how does it manifest in other physical properties, things you care about, like the motion of electricity, the motion of heat? Okay, so what I'd like to do now is tell you how to measure this in the lab. This may sound hard to do because I sort of set the whole thing up as going forward and backwards in time. Now, I don't know about you, but I find it difficult to do that. But it turns out people have actually been doing this for a long time and are doing it even more now. And the earliest version of this is something called a spin echo. So I'm going to explain to you now what that spin echo is. Actually, while I was preparing this talk, I found this really nice vintage Physics Today cover. Physics Today is like a magazine that explains what's going on in physics to a relatively broad audience, from 1953, which explains how the spin echo works. So let me set the stage for you. So you imagine you have a bunch of runners here on a track. And actually, you can think about this track as the equator of those qubit sphere that I drew for you before. So that's what this track sort of actually literally is that equator. And these runners, they run around the equator. That's the quantum particle changing its state in some way. But the thing about these runners is that they start all lined up like this, but they all have different speeds. So some of them are fast runners, some of them are slow runners. And so when the referee tells the runners to start, they start running, and actually they all run at different speeds. And so after a while, in this stage C, the runners are kind of spread all over the track. So where they were nicely sort of lined up here, kind of easy to see, here they kind of spread everywhere. But now, let's suppose at this point, the referee again sends a new signal. The new signal tells all the runners to just reverse direction. That's the signal. And what's going to happen? Well, some of the runners are very far along the track. Some of them didn't get very far at all because they're kind of slow. But the fast runner, although the fast runner has more ground to cover, the fast runner is faster. Okay? And the slow runner has less ground to cover, but they're slower. And precisely because they run backwards at the same speed they ran forwards, as they run backwards, they're going to recollect and all line up again at the starting point. So you can actually try this. It works, at least sort of. I would do an experiment for you here, but I don't have enough space. The key point is that actually this referee who tells the runners what to do can tell the runners to reverse without knowing precisely what their speed is or even where they are. He just gives a signal so that everyone reverses at the same time. So that's the key thing that this referee can do. So for example, you could imagine they stand in the center of the track and send out a pulse of sound that everyone is going to hear at the same time. And then no matter where they are, how fast they're going, they just turn around and go back. Okay, so this is a possible experiment to do. Let me show you more of my PowerPoint animation skills. So here's my runners lined up. They run forward at different speeds. Then I send the reverse signal, and they run back, and they all line up again. And this is real. So PowerPoint has like a speed setting, so it's the same speed forward and backwards. So like I really did the experiment for you. It actually works. At least using the tool of PowerPoint. Okay. And you can measure this. So this is something that you can measure. Actually, this is sort of the start of a set of technology that is, for example, used in MRI machines. Because what these runners were originally were actually spins in nuclei. And you use these spins in nuclei to image things in your brain, for example. So this is actually the first data collected by a person called Erwin Hahn in 1950. And you could think about these different spikes as like the lining up. So this is sort of starting out all lined up. And then the referee is the experimenter sending some signal which causes these qubits to reverse, the runners to reverse in the right way. And you get this series of peaks, which is the sort of recollimation, everybody lining up again at certain well-defined intervals. Okay. But the clever among you will note that the peaks are getting weaker and weaker as you go longer in time. So what's happening? Evidently, we're not lining up perfectly if we keep doing this over and over and over again. Well, let's go back to our cartoon. Suppose they run forward. The referee says reverse. They go backwards. Okay, but now they end up in totally different place. Some of them make it back. One of them actually got a little bit too far, and two of them are a little bit slow. Well, what happened? Well, if we look in detail, we look at the sort of movie of the race, we find that, well, actually what happened is these two qubits, these two runners, interacted. Maybe they bumped into each other accidentally on the way there. So they didn't do it going out, but they did do it going back, so that gets an asymmetry. It means that they didn't exactly undo what they did when they were running on the track. And maybe this runner, there was a gust of wind, a favorable gust that pushed them a little bit far ahead, right? So this external force of the wind caused this runner to go a little bit faster, and so it caused it to fall out of alignment. So if there was a headwind, say, this way, then you can go slower this way and faster this way, and you wouldn't line up exactly in the end. So this tells us two things. It tells us, first of all, that in order to see any kind of signal for a long time, we're going to have to make sure that there's no analog of the wind in our system. So no external thing which influences how far my runners are going to get. And the second thing is, if we want to study these interacting qubits, we don't just want to have these runners running by themselves. So if we want these kind of interactions to happen, then we have to have a system where we can make sure the interactions happen both going out and coming back. That when they bump together, they do it in a time-symmetric fashion. So they bump going out and also do the reverse bump going back, and then they'll indeed get back to where they started from. Okay, so what we need is something that can take a complicated quantum many-body system, a system of many qubits, and perfectly drag it back in time. Okay, so We need a time machine. And this is part of the thing that I've contributed to this story, is to think about how these kind of time machines could be possible. I showed you that it is actually possible, or at least I claimed it's possible, and showed you some data for these non-interacting particles. But what about if I have the interactions? It turns out that it is possible, rather remarkably. We can build these kind of time machines in the lab. So here I'm going to show you a setup from your neighbors in Boulder, from NIST, and the group of John Bollinger. This is a really nice experiment that's ongoing, that we discussed this week actually at the conference. So it's a hot topic. And the idea of this experiment is I want to take my ions, my beryllium ions, that's going to be this blue cloud here, and I have some kind of big device which is going to confine these ions in a small region that I can manipulate them and work with them. The way that you confine them is using this gigantic magnet here. So this is a huge superconducting solenoid, meaning it's a bunch of wires wrapped like this. The magnetic field here is like stronger, by a factor of 4 than most MRI machines that you may have. So those are already like really strong magnet. You can't have any metal near them or it causes a huge problem. This is even more dramatic. And using the laws of electromagnetism and the motion of particles, one can show that when you have this really strong magnetic field like this, like a big super strong magnet pointing up, then these charged particles want to sit in that field and they want to spin around. So actually this little cloud here is spinning. This is a pretty big sized object here. This is some kind of ordinary sized table. This is a little 2 centimeter thing that's stuck down inside of this. And there's a very high vacuum inside of here. And you just want to isolate these beryllium ions as best you can. This is what it looks like ultimately. So this is the picture I showed you again. This is actually an experimental picture. These beryllium ions form this very nice crystalline structure inside of this big magnetic trap. Okay. And these arrows here are meant to indicate that up or down or 0 or 1 configuration that these ions can have. Okay, so these are our array of qubits. They're very well isolated. You can control them by sending in microwaves and doing other kinds of manipulations. And you can actually make them talk to each other in the following kind of amazing way. This crystal can actually vibrate. It's a little like two-dimensional layer of ions. It can wiggle like a drum head. And when this whole drum head wiggles, all the different ions couple to that wiggling. They feel that wiggling in some way. And so if you can kind of drive the wiggling of that drum head in the right way, you can make all these different ions talk to the drum head and then talk to each other as a 2-step process. And by controlling the way that that drum head moves, technically what you're doing is you applying some lasers. You can change the color of those lasers and you can actually effectively cause the interaction between these different ions to go from running forward to running backwards. Okay. So I'm not going to explain in detail how that's done, but it is possible to do. And actually they have reported experimental data where they've carried out this kind of fast forwarding and then rewinding procedure for a very simple kind of model, very simple kind of system of basically 100 or so of these beryllium ions. Now the system that they studied so far is not really fully chaotic. So they can do this experiment of going backwards and forwards, and they see that the butterfly doesn't grow as much as you might think in a fully chaotic system. So they can actually see that it's not completely chaotic. But they're working very hard to push the technology and eventually to study a very chaotic system, and then they try to see this growth that we talked about on the previous slides. Okay? So that's how you measure it. Let's talk about what it has to do with other physical things. Okay, so let's talk about speed limits. When I was a kid, I really wondered, do they drop bombs on you if you go too fast or something? What's going on here? I guess they just time you, right? If you cross some point and they time you, if you get to the other point too fast, then they know you sped, and then the airplane can tell the cop car to come get you. Okay, so it's interesting that we have these speed limits, and it's interesting to ask, what enforces them? So there's one universal speed limit. It's this number. Anybody know what this is? It's the speed of light in miles per hour, which is a terrible unit to use for the speed of light, but anyways, that's what it is. 670 million miles per hour, roughly speaking. Okay, that's the ultimate speed. As far as we know, nothing can go faster than that. But of course, this is not a speed that you encounter very much in daily life, right? Normally, you have something more mundane. And what's enforcing this is the cops and the government. But in these systems of many interacting particles, we can also have new kinds of speed limits emerge. So the speed of light is always a fundamental speed limit, but maybe you can have a different kind of limit on how fast you can go. So for example, this person is experiencing an emergent speed limit due to this strongly interacting collection of sheep here. Right? They can't go very fast, even though maybe the 50-mile-an-hour limit is over here somewhere. So what we're interested in is the same kind of physics, except where these are quantum sheep. Okay? And so, what does it have to do with anything? Well, you think about like this blue car is like an electric charge trying to make its way through some system. You want to have electricity flow through your wire. You need to get electric charges from one end of the wire to the other end of the wire. But if there's like a lot of sheep in the way, then it's very slow and hard to do that, and it has a high resistance. So in particular, if we want to understand how that resistance behaves, say as a function of the temperature of the system, we need to understand how these sheep behave, these quantum sheep. Okay, and one of the ideas going around that's being discussed at the meeting this week is that maybe this spreading of chaos, this quantum butterfly effect, could give you a speed that's relevant for, say, the motion of electricity or heat energy in your system. And in fact, we've sort of seen that already. If we go back to this picture of the growing blockage, we had the butterfly here, and it spread over the whole system in this way. But if you look at this, every unit of time, you're going 1 unit of space. Every unit of time, 1 unit of space. That's a speed. You're increasing your distance as you go in time linearly. So actually, this slope here defines an effective speed at which this butterfly effect moves outward in the system. And one of the ideas being discussed is that this so-called butterfly speed, the speed at which the butterfly moves outward, could be relevant, could be related to the properties of, say, the motion of electricity in your system. Okay. So you have some strongly interacting, very hard to understand, chaotic mini-qubit system, but maybe this butterfly speed gives you a way of understanding how, say, heat or electricity move. And maybe you can use that to say something interesting about a mysterious material property. So for example, there are a class of materials called high-temperature superconductors. These are materials that superconduct at relatively high temperature. Most superconductors that we knew of before the 1980s would only superconduct at just a few degrees above absolute zero, so very cold. These so-called high-temperature superconductors can do it at hundreds of degrees, almost closing on room temperature, although not quite there. But they're very hard to understand. It's hard to understand the way electricity moves. Suddenly it starts to move freely in the superconducting case. There's no resistance. But above that state, electricity seems to move in a very strange way. And so one of the ideas that people are thinking about is whether, again, this butterfly speed could be related to the way that electricity moves. Now, the final topic I want to talk about tonight is something a little bit more esoteric, but also very interesting, which is the subject of black holes. Okay. So here's a sort of cartoon, an artist rendition of 2 different black holes, actually sort of spiraling into each other. This is a snapshot of that. And what are black holes? They're essentially objects that's predicted by Einstein's theory of general relativity, which is our current best theory for the way space and time behave. And they're essentially regions of space where light can never even escape. So even if you go at this maximum speed limit, you can't get out. That's why they're black. Now, it turns out actually that once you include quantum mechanics, they become not so black anymore. but that's for a little bit later. But rather remarkably, you can actually look up in the sky and see these things indirectly via the signals they send out into the universe. So there was a spectacular development about 2 years ago now, 3 years ago actually, in which using these incredible instruments. So this is a picture of an instrument called LIGO, which sits in the desert of eastern Washington state, and has these two great big long arms. And it sends light up and down these long arms. And the idea is that when space-time ripples in some way, when you have a wave moving through space-time, these arms change. They expand and contract very, very slightly, a super tiny amount, but in a way that you can actually detect using this very sophisticated instrument. And you can see that gravitational wave, that ripple in space-time moving through. And once you detect that ripple, you can actually go back and find signatures of this, say when these two black holes merge together and collide and to form one black hole. They release lots of these space-time ripples, they travel to us, and we can observe them with this rather amazing instrument here. In fact, I was able once to go in the control center of this thing, and it's really amazing. They have this real-time plot, and they can show you like the traffic in LA. They claim they can even see tumbleweeds hitting the side of this thing. So that's how sensitive it is. I mean, it's just like mind-boggling that it's possible. But nevertheless, it is. There's another corresponding device in Louisiana. They're separated in space so you can tell whether something's happening from a distance away or from happening locally. And they took this data in actually late 2015, September 2015. They measured the signal, the differential change of these two things, these two arms. They got this signal from the one in Washington, this signal from the one in Louisiana. They lined them up with a slight time delay because they're separated in space, and lo and behold, they more or less match, right? And they also match the prediction of Einstein's theory. Yeah. Okay. So what this tells us is these black holes, we can directly see them. And you may note here that the decay at the end looks like there's some kind of big ringing up, and then things decay back down. That decay may remind you of the decay that we saw in the spin echo, where the signal would get smaller and smaller. And in fact, we understand now that this is sort of the same thing, that actually these black holes, in some sense, can also be regarded as quantum chaotic. To make sense of that, we actually use a sort of toy model. Those black holes in real life are too hard to understand. So like, instead of starting your life doing a mountain bike down 15 degrees, you start with training wheels in your driveway. So we use this toy universe, came up with by Juan Moldacena, who I think you heard from last year or the year before, in which space-time has a kind of funny curved pattern. It's like this disk where all the fish are the same size. This is a famous drawing due to Escher. And you can also put black holes inside this funny space. And this space is nice because in the interior here you have gravity. And what Moldacena told us is that that's exactly equivalent to some other system without gravity, which you can think of as living on the edge. So we can actually map the quantum properties of gravity here, is what we want to understand, the quantum properties of a black hole in this space, to the quantum properties of the boundary. And when we do that mapping, we find something remarkable. It turns out that as a particle falls into the black hole is pulling more and more, and it gets accelerated more and more. And in fact, its energy, in a certain sense, doubles every unit of time. That doubling of energy may sound familiar. That's what we saw also. There was a doubling of the perturbation in the butterfly effect, and also a doubling in this case where everyone could talk to everyone. And so, in fact, one of the very remarkable developments that we're also discussing at this meeting is the understanding that actually this spreading of the effect of the butterfly in this non-local, where everyone can talk to everyone model, this doubling of the size every time step is actually precisely the same as the doubling of the energy that happens here. And so we have this kind of new microscopic particle-like picture of the understanding, which gives us some new understanding of the way, that things fall into black holes and what that might mean. Okay. So with that, I'd like to just stop and say, what do we do? I tried today to give you some kind of pictorial representation of the quantum butterfly effect, and to give you some sense of how it manifests in different kinds of systems. And this is just one part of a much bigger story. So this is not the only kind of thing we're talking about at this conference this week. And there's a lot of interesting stuff. The subject of quantum chaos goes back a long ways. But there's been a really exciting revival of interest recently due to all these new connections between black holes and materials, between information, and at the same time, new experiments that we can do that I showed you a small taste of, which give us the ability to actually probe this physics in the lab. Okay, and these are my collaborators with whom this would not have been possible. So thank them and thank you for listening.
Well, thank you very much, Brian, for a very beautiful
thanks.
talk. And I'm sure there are questions, so please, Brian will be happy to answer.
How old were you when you knew your mind worked this way?
So I'm supposed to repeat the question.
You have to repeat the question.
So the question is, how old was I when I knew my mind worked this way? I don't know. I think I actually came to physics pretty late. Even in high school, I actually wanted to be a medical doctor. But then I read this book about Maxwell's equations, and there was this amazing pictorial picture where you just have this upside down triangle. So electric field is called E, magnetic field is called B. There's upside down triangle, and it's like triangle E equals something. And supposedly this explained all of the universe basically. So that was just fascinating to me, and so I kind of just went down the rabbit hole and never came back. Yeah.
Oh, he's very much here.
There was a report just this morning out of Newsweek about a team of physicists interested in Russian and American, and they were announcing that they had gotten a quantum computer device of some kind to actually reverse time, which seems connected to what you're saying. I wonder if you'd heard of that, and can you explicate that brand new news in any way?
Yeah, so the question was, there was a report this morning or recently in Newsweek about a team of Russian and American scientists that also reversed time using some kind of quantum computer-like device. Yeah, so the basic answer is that, so I didn't look at that report yet, so I haven't had time to tell you in detail. I can't tell you in detail what they said, but it's very much connected. So the set of sort of tools, the degree of control you need over a system to run a quantum computer successfully is the same kind of control you need to do this backwards and forwards evolution. In other words, if you can do anything you want to the system, you can certainly do something forward and then backwards. And so the same kinds of tools that they're probably using are the kinds of tools that were used in the experiment I showed you here from Boulder, where they're somehow manipulating the system in a coherent way, and they're able to control effectively the evolution. And so in fact, probably they're interested in some signal which could be related to chaos in some way. So I don't know exactly what they were looking at, but I would be willing to bet that that kind of signal would be also a probe of chaos.
If I may add, the statement "time runs backward" is a bit fanciful. It's when the runners went backwards around the track, you don't think of that time running backward. But that's closer to what's actually happening in the quantum system.
Yeah, it's like, of course, the time of sort of everything always goes forward. But what we can do is sometimes take some stuff and isolate it well enough so that we can effectively rewind time for that set of stuff. And that's what they're doing in this experiment. They're not really controlling the flow of time of the whole universe.
What does this do to our thinking about the second law of thermodynamics?
Great question. So the question was, what does this do to our thinking about the second law of thermodynamics? So the subtext there is the second law says that basically things are irreversible. You sort of can't go backwards. And that law is still totally safe. We're certainly obeying that law here. The idea here is that although we're rewinding a small thing, it's costing us a lot of energy to do that. So we have to have this very complicated apparatus that's running, and the net change in irreversibility is still positive. So it's still irreversible, it's just that you're using a lot of resources elsewhere to locally reverse a small region, and that's totally allowed by the second law.
Okay, well,
All right,
thank you very much, Brian,
thanks.
for a wonderful talk.